So now that we have some understanding of how a molecule can emit light, let's think about emission spectroscopy, right? So with absorption, it's a little bit more straightforward in that the molecule just absorbs the light and we look at the light that's missing. With emission spectroscopy, we need to understand a little bit about these processes to understand exactly how to look for the emission of light and whether it's possible for all molecules. So fluorescence in particular, right, the faster of the two processes, is highly useful for analytical purposes. Right, it's a good way to measure concentrations. The main drawback to fluorescent spectroscopy is not all molecules fluoresce. So that limits its usefulness because you do have to have molecules that fluoresce, right? Some molecules just undergo the intersystem crossing and you see no light that comes off of them. So you do have to find something that has fluorescence properties to be able to observe it via emission spectroscopy or phosphorescence, right? It could have phosphorescence as well. So that does limit the scope of emission spectroscopy. The one option is you can, at least particularly in biological systems, is you can attach something to your molecule that does fluoresce, and that allows you to keep track of it. And this is a really powerful technique that's used in biological chemistry, particularly with things like the green fluorescent protein GFP that Mark studies. And that's why its discovery led to a Nobel Prize. So anyway, why is fluorescent spectroscopy so great though? What makes it so useful? One of the big advantages fluorescence or emission spectroscopy in general has is that it's more sensitive than absorption spectroscopy. And let's think about why that is. Again, sensitive meaning that it can measure much smaller concentrations of material. Let's think about the measurement that we're making. All right, absorption spectroscopy. So in absorption spectroscopy, the idea is we have a light source. So I'll just draw a little light here, right? And that we shine that through our sample. Put the monochromator in there. And we're looking at this bright light source and seeing the missing light, right? How much less light. So if we sort of make a plot of signal versus wavelength or whatever, if we have a large amount of signal, and then if we have any absorption, we see a small dip in this. But we start from a high level of light and only see a small decrease in it. For fluorescent spectroscopy, on the other hand, our sample is our light source. Right, we often have to excite it with some other light source, so maybe we do still have a light bulb. And we'll look at this in just a little bit. We shine some light onto our sample, but it's our sample itself that's producing the light. And we see that with our detector. All right, these represent our detectors. And if we think about our signal versus wavelength, right, so I just need to make this clear. This is the background, right, or our blank, and this is with our sample. With fluorescence spectroscopy or emission spectroscopy, our background signal is nothing, right? We just have no signal coming from our sample. If there's nothing that fluoresces there, we just get zero light. Whereas once we have sample there, we're going to have an increase in signal from nothing. So this is a lot easier to see, right? It's like looking for a small source of light in a dark room, or instead of looking for how much does your light get dimmer in a bright room. Right, it's a lot easier to see that starting from nothing, that there is something, than to go from there's already lots of the thing and you're trying to look for how much less there is. So that allows you to measure things at a much smaller concentration because, it's because of that low, this is what's known as a zero background technique, meaning you don't have any background signal to worry about, in theory. In practice, there's always a little bit. But when you have zero background, it's much easier to see a change from zero to something than from a large amount to nothing. And so this means that fluorescence, emission spectroscopy, has been demonstrated down to sort of the single molecule level, where you can measure just the presence of a single molecule using fluorescent spectroscopy, which is really amazing. You cannot do that with absorption spectroscopy, I can tell you that. In the next video, we'll look at how do you actually set up an instrument to measure fluorescence or emission spectroscopy.